Hi, and welcome to this section of the Calculus 3 tutor. And in this section of the class, we're going to continue talking about double integrals, which we started in the last section. And in this section, we're going to talk about double integrals in polar coordinates, okay? So from the last section and through this one and into probably the next 3 or maybe 4 sections, we're going to be talking about multiple integrals, double integrals. Eventually we'll get to triple integrals in the next section and the sections following, okay? The thing to remember is once you get the hang of what this double and triple integral stuff means, which we already did in the last section, okay? Doing it in polar coordinates and doing it in later on when we get to cylindrical coordinates and spherical coordinates and all of those things, the math just looks a little different, but it's exactly the same concept, okay? So once you understand the concept of what a double integral is, then doing it in polar coordinates, yeah, there's a little things you need to understand, but it's not that big of a deal to do, okay? But you really have to understand what you're doing, okay? So just to recap, we did a double integral in the last section. We did several problems with that. And what that is you have a function of two variables, x and y, let's say. This is the last section. You know, you have your x, your y, and your z going up. And this function is a function of only two variables. So the x, y numbers in the plane are your independent variables, okay? F of x comma y. And the function, quote unquote, hovers over the x, y plane. And that's the function that you plug in your x and y and you get a number z that corresponds to what the function is equal to. So when you're doing double integration in general, and when we did it in the last section, all we're doing is we're looking at that function that's hovering over the xy plane, okay, and we're integrating along x and along y, and we're basically smearing an area in the xy plane that we're trying to integrate this function over. So you have this function, if this piece of paper is the xy plane, this function's hovering over the xy plane. We're defining some area, literally. It could be a rectangle, could be between two functions, it could be any shape you want down here in the xy plane, and we're going to integrate, in other words, we're going to add up the values of this function that correspond to what's the values of x and y that we've defined, that it traces out over the xy plane, okay? So that's what we're doing. We're you know, instead of just in Calculus 1 when you have a function and you integrate between a and b, or x is equal to some number and x is equal to another number, and you're integrating between two functions. When you have a function that hovers over the xy plane, a function of two variables, you can't just define x or y, you have to define an actual area that you're going to integrate this function over. And that's what we did. And we did it by defining the functions in the xy plane that we were going to define our boundaries, and then we just did the integration, you know, the innermost integral and then the outermost integral, okay? This section, dealing with double integrals in polar coordinates, is exactly the same thing, okay? So don't think that this is just some crazy new topic that's just different. It is exactly the same thing, the same concept. The only difference is, instead of a function of x and y, which is what we were dealing with last time, we are going to choose to represent these functions in terms of r and theta, which you may remember from previous courses. That's how you represent a number in the polar coordinate system. Instead of x and y, you have r, which is a radius, and theta, which is an angle. I'm going to draw all this for you, but that's what we're doing. So instead of defining the area in the xy plane that we're integrating over in terms of x and y, we're going to define it in terms of a polar function r and theta. But then after that, everything else is the same. You take the innermost integral and the outermost integral. And that's why we're doing. By the way, why do we even do this? Why aren't we just content with learning how to integrate like we did in the last section? Well, the reason is because certain integrals, usually the ones that have a circular symmetry, maybe they're circular symmetry, maybe they involve circles. Polar coordinates, polar integrals yield much simpler integrals. That's just really the bottom line. And you'll see in a minute, but when we start writing integrals in a polar coordinate system for certain functions, it's going to be really easy to do. But if you were to do it in x and y coordinates, Cartesian coordinates, the math would be messier. And so that's why we learn how to do it, because it makes our life easier, okay? So let's do a little bit of review of polar coordinates and just creep our way on into talking about the actual integrals, okay? So remember back from a long time ago, you learned at some point, maybe in a geometry class or a trig class or even your calculus class, you learned that about the polar representation of a point. But even before we get there, if this is your x coordinate and this is your y coordinate, okay, and you have a point here that you care about, this is the point you care about, you already know, because you've been doing this stuff a while, that you can define an x coordinate, an x coordinate here, and a y coordinate. So this distance between this axis and this point we call it x, it's just a number, and we'd call this y, it's another number. And these 2 points, x comma y, define uniquely where this point is, and we call this Cartesian. All right, Cartesian coordinates, okay? Now, a long time ago, I know you probably already learned, but we're going to review it here, that there's an alternative way to represent a point in a plane, because this is a point in a 2-dimensional plane, right? So again, this is x, and this is y, okay? Same thing, I haven't really done anything different. And again, I'm going to put the point in exactly the same place, so I really haven't done anything new or different or otherwise scary or frightening, okay? But what I'm going to do is, instead of defining this point in terms of x and y, what I'm going to do is I'm going to draw a radius vector from the center, from the origin, to this point. It's supposed to be right on top of this point. And I'm going to call the length of this thing r. It's just a length. It's an arrow. It's basically a sort of like a vector, but it's even easier than that. Just think about the distance between here